This chapter, we'll start with exponentials. Have you seen these before? It would be something like that.
Yes.
And the shape of the graph
Is that
will look like this. Good parent functions, right?
Yeah.
Do you include that?
Yeah, no, I don't either.
It's been a while, but okay. So an exponential function. Exponentials and logs are very useful in science. Because if you're headed for a science career, these are going to show up a lot. Exponentials show up a lot in population growth. Okay, so if you look at the population of the Earth, the general trend of population in our planet is following an exponential curve. Now, can we sustain that on forever? No, we can't. It's not physically possible.
Right now, we're not even sustaining it.
So you have times in history where population's taken a dive, like World War II, like 15 million people died. Right? That's a lot of people. It's going to affect this a little bit, but again, the general trend, if you look at the trends from the population estimates from like time zero until now, it pretty much follows this. And most of this is in the last 100 years, believe it or not. Okay, that's what an exponential function is. You have a billion people, and if each of those people have a child, you now have 2 billion people. And if each of them have a child, then you have 4 billion. Okay, see how it grows.
Yeah.
It's an exponential function and population grows. Okay, it does get a little bit more complicated than that, especially when you get into like wildlife biology and managing populations. You have something called the logistic equation.
What is that?
The logistic equation adds carrying capacity. It adds all sorts of habitat factors, so it does get a little bit more involved, but again, you see the general start of a population growth, but then it will hit carrying capacity and hopefully level off. What happens if a population's above carrying capacity? Hopefully it's going to do that. Okay, but then you bring predators in the equation, and it can really dive. Okay, and it can come down here, so there are a whole bunch of factors that have to be considered and stuff like that, but exponential equations do come into play. Okay, so just a little bit for you there. Exponentials. Okay, so if you want, one way to graph these is with the table values. Okay. So I have put a general curve up here for 2 to the x, but I haven't been specific with my points.
So
if I plug -2 in, what's 2 to the -2? Knowing our work from the last couple days. No, -2. What does the negative exponent do to
it's 1 over.
AJ? Yeah, so 1 over 2 squared is 4. Okay, so -2, this point would be -2 1/4. Okay. About -1. 1 over 2 to the first, right? Which is 1/2. Let's see your exponent properties. What's 2 to the 0? Always. 2 to the first, 2 to the second, and then if you did 2 to the third, you can see now this is going to start growing really quickly when you start mounting these points up here. So that's a general exponential. That's your parent function, basically. We can write it like that. Okay, this is our start value. Right. So if you have a number in front of the exponential, that's your starting value, that's your y-intercept. So that would be this number right here. And then of course you have your growth constant. Again, times 2, right? Times 2, times 2, times 2, growth constant. And then your exponent. Any one of those can change to affect the model. Any questions there? What is, so I can still ask you questions like this. What's the domain of y equals 2 to the x? What's the domain of 2 to the x? It's all the x values possible, right? Can it go to negative infinity?
No. Yes.
Can it go to positive infinities?
Yes.
Yeah, we can plug any number in there. So the domain is all real numbers.
It's all real numbers too, right?
No.
It's, it would slowly approach 0, right? It would never reach it, right?
There's a horizontal asymptote at 0, right? Never crosses, so what's the range?
So 0 to positive.
Yeah, you can write x equals 0, or you can write 0, oh, sorry, y. Or y. Again, in this one we can write, we can also write it like this. And this one we could write like this. And again, just remind yourself all the different ways we can write those kinds of things. This is the most common interval notation. It's the easiest to read. Is that function increasing or decreasing? Yes, it's strictly increasing. So it's always increasing, right? Left to right. Always going up. Okay, so this is strictly increasing.
So,
Okay.
you know how in different countries they use right to left? Does everyone different equations going right to left, then it would be increasing? Like, do they graph the same way? Like right to left rather than left to right? What's actually the question?
I don't know. In Arabic, you know, like Arabic writes right to left. I do not
Or
know.
like Chinese?
I would doubt it, considering the universal nature of math. I would expect that left is still negative, right is still positive, and it would have the same structure. You almost have to, but I do not know for sure. Again, horizontal asymptote, we already mentioned this. Y equals 0. Is there a maximum or minimum?
Oh, yeah.
Does this ever have a maximum?
No.
No, it keeps going forever, right? Okay, does it ever have a minimum? I heard yes and no. Is 0 a minimum? Does it ever reach 0?
No.
Okay, so it cannot be 0. But if you pick a low point on that graph, can you go to the left and get lower? There's no minimum. Okay, no maximum, no minimum. There's a low, this is called a lower bound. It will never go below it. Right, but there is no minimum value specifically. What? Mass extinction, you would die. Thank God.
Whoa! it would go up, this isn't accounting for
This is not,
population.
yeah, this is just, right?
No, he was saying, it-
So what would happen in a mass extinction? This is a good question. Population's coming here, what happens in a mass extinction? Bye-bye, right?
no, but that's only with this, that's a
That
total
would be
different.
total
equation.
extinction.
It's not like there's a human that can't die.
Okay.
That's a different equation. Different equation.
Let's do a couple more graphs and then we'll get to this.
Which are cost.
It's a good question. Okay, knowing your function, the parent functions. Okay, what does that do?
Goes from right to. Wait, oh, no. It
Okay,
goes
so
down.
consider that versus
Up to, sorry.
that. So yeah, this is paired with the x, right?
Right,
So this is going to be an x movement, which direction?
left. Right, off.
Right, too, remember? It's opposite line. And this is going to be, no, it's not with the x. It's a y movement. Yeah, it's a down two. Okay, so parent functions still come into play here, where if it's connected to the x, you have an x movement, and if it's not in the x, this is a y movement. Okay. So if I graph 3 to the x, generally the parent function would look like this, right? But I'm going to move it down 2 units, and now there's my new graph. Okay, versus this is going to move right 2 units, not left. And it's still going to travel the same, but we just move this spot right 2 units. Okay, so you can still use your parent function knowledge in this. So let's get those down. People say picture the old sheriff of Nottingham waddling down the street.
Heck, yeah.
Doodle-eye, doodle-eye. So, how does that change? Look at that. What did we say this number in front was? Start value, right? Okay, so this start value is 4, that's the y-intercept. That means this function, we have a y-intercept at 4. Again, same shape, we're just moving it around. Okay. Okay, so here's a good one. What about this? What does the negative do to an exponential? Is it down below? We can write this such. You know what that looks like?
Maybe like this.
Yeah. Changes it. Remember, a reflection over the y-axis. If you put a negative in with the x, it reflects it over the y-axis. Okay. So again, more parent function stuff. This is what we would call exponential decay. No crisis is what you're in. Okay, exponential decay. Scientifically, anybody think of a possible application?
Half-lives of uranium.
Yep. radioactive decay, half-lives, carbon dating. Any of that stuff deals with exponential decay, because supposedly, now we haven't been around long enough to measure this, so it's a scientific, educated guess.
So we've been like,
These, like carbon-14 will degrade so much every,
10 years.
I think what's half-life, 3,000 years or something like that. Half of it will be present in 3,000 years, and half of that will be present in 3,000 years. Remember the decay constant is halving every several thousand years. Okay, so exponential decay, we would call these exponential growth. How many of you have had an infection and they've swabbed it and done a culture at a hospital or a clinic? Okay, stick it in your throat, put it in a petri dish, and the bacteria starts to grow exponentially. And when there's enough of it, they can say this is what it is after looking at it at a microscope. It's an exponential growth application. Probably, let me make sure. Tomorrow you'll have a little more, but yeah, that's it for today. So, things like, so some of the more popular AP calculus questions, like, involve some of this stuff, like how fast is coffee in a cup cooling? That's an exponential decay. So it is what it is, but there's a question in here just like that. So what is the temperature of coffee after 15 minutes if you have an exponential model? Or stuff like that. Yep. Nice thing about calculus, we can find out how fast it's cooling too. Very easily. Okay, I'm done. Ethan, you hand me that paper. Yeah. I'm going to write down today and tomorrow's work. Tomorrow, I posted a video on Google Classroom. It's a video from last year, just like we're doing now, for you to watch. So make sure you have your Chromebooks, maybe some headphones, or the sub can put it up on the screen. But this is both assignments for 2 days. It's not due until Tuesday. So today,
Mr. Archer,
what?
will you have class on Tuesday?
Tuesday's the 9th.
Which is the SAT?
Yeah, no, we won't. You won't see it, so it's going to be due Wednesday. That's when the state says they're going to do it, so that's what we do.
Good job.
So you have, this is today, tomorrow, and then spiral through Wednesday. Okay? So, should be plenty of time, almost a week to get it done. Again, if you want to watch the video at home and work in class tomorrow, more power to you. Just make sure that you're using your time wisely, because I will not be here to hold your hand.